Good morning, everyone. We will continue inverter-based amplifier. We want to use a CMOS inverter as an analog amplifier. Yeah, then we have two advantages. One is a very low input noise voltage. Actually, the other is low power and high speed. Say, for a given power budget, we can maximize the speed by using inverters. Yeah, for a given speed, we can minimize power by inverters. There are two advantages of CMOS inverter amplifier. Yeah, problem is it's very sensitive to supply noise. We can solve it by using voltage regulator. Also, it's very sensitive to PVT variation, process variation, supply some temperature variation mismatch. That's a problem we have to solve by using circuit techniques. Okay, so yeah, we have seen the IV characteristic of inverter in the previous class. So DC transfer curve is 0 to VDD, 0 to VDD, and then yeah, this is my DC transfer curve. We want to use this operating region for amplifier, for amplification. And so usually, see, we can find, say, if the cross section of this DC transfer curve with a VO equal VI straight line, that's called the logic threshold, right? This is called the logic threshold voltage. So we want to operate inverter at around the logic threshold voltage. Okay. This logic threshold voltage, see, if there is PMOS and MMOS, okay, this is my CMOS inverter, and then the logic threshold voltage can be calculated by square root mu n Cox W over. This is MMOS side. Mu P Cox W over L. That's a PMOS side. So then we have mu n Cox W over L times I think this is MMOS threshold voltage, right? That is, yeah. And then there is PMOS threshold side. This times so, you know, if my MMOS is stronger, see, if this mu n Cox W over L is larger than PMOS counterpart, then the logic threshold voltage will be shifted toward VTHN. Okay. If PMOS is stronger, this logic threshold voltage will be shifted toward VDD, right? So this logic threshold voltage is very sensitive to those variations, right? Mobility. Yeah, those mobility is proportional to around 1.5. I'm not sure exactly. So mobility is reduced as the temperature is increased. They have around the same behavior. But if there are some mismatches in channel lengths, then logic threshold voltage will change significantly, right? So it's very difficult to track this logic threshold voltage. We need some circuit technique, yeah, to track this one. Okay. Yeah, one way to use this CMOS inverter as an amplifier, maybe something like that. Yeah, I have a capacitor coupling here, and then see, I just maintain this input DC level at the logic threshold voltage by connecting this inverter. Yeah, the equivalent circuit of this one will be like that. So this resistance will be those yeah, those transconductance values at the logic threshold, right? So at the logic threshold, see, you can calculate the GM. Yeah, those GMs are square root 2 mu Cox W over L ID. Or you can also represent it by ID over 2 half VGS minus VTH, right? So this VGS will be my logic threshold voltage, okay? This is a strong inversion equation. All right, let's just see by sigma spice whether this one works or not, okay? Yeah, let's just see. Yeah, let's copy a netlist. Where is my netlist? Yeah, this may be. Okay, this is fine. Okay. Oh, I have some netlist here. Okay. Now let's edit a little bit. Now this is an inverter-based amplifier 4 maybe. Yeah, I have some sub-circuit here. You are familiar with this sub-circuit, right? Oh, this is somehow inverter small. Just so we can say just inverter. Oh, maybe. Oh yeah, inverter, just inverter. This may be inverter large. Okay. How come this is? Oh yeah, I just copy this one and make a multiplication. So if I put M equal 10 here, oops, M equal 10 there, this is just a parallel connection of 10 transistors here, right? So this I can say inverter 10. Because 10 inverters are in parallel connection, okay? So my VDD is 3.3, and then I will put my Vin is in 0 DC 0 AC1 or maybe sine wave 0. 0.1 millivolt and then 10 kilohertz. 1 kilohertz. Okay, so I have a huge capacitor. This into huge, and then I have an inverter. Inverter is into DD just inverter. And then I have a amplifying inverter which is into out DD inverter 10. Okay, then yeah, then I have some. Oh, is it right? Tran. Yeah. Say 1 microsecond to 5 millisecond to 1 microsecond or 0. Start the 0, 1 microsecond, and then dot print tran. V in, V into, V out. Okay. That end. Will it work or not? Okay. Okay. Oh, I don't have that. I will open something. I have to go C. Where is my C folder? Oh, I don't have a C folder. Oh yeah, here. L24. Okay. Can I edit? Oh, it's not open. That's the problem. Oh, it's gone again. C folder, L24. I have to open something. Where is my inverter MP3? Okay, edit. I just replace everything by that. Oops. Okay, this is my inverter MP3 4. Alright, fine. So can I edit? Oops, it's gone. 4. I have to open 4. Where is my 4? Oh yeah, here. Okay, now I got it. Let's simulate it. Try to grab it. Is this L24 and C? Oh yeah, that's good. C. So I will put my input is here. My output is there. Oh, my output is not very good. It's distorted already, right? So where is my into? So my into is there. So it's too large. It looks like it amplifies pretty well, right? So let's reduce this 100 millivolt into 10 millivolt. Okay. Now it looks okay. Eh? Where is my in? Well, my in is very small, but oh, it's distorted a little bit already, right? My output is distorted a little bit. Because somehow it's too large. Gain is pretty large, right? The gain is pretty large here. So you can watch, see, if I put AC analysis here, do I have AC? Oh yeah, AC one there. So instead of tran, I will try AC analysis. For the AC analysis, see, I will dot AC, decade 10, 1 hertz to 1 gigahertz, dot print AC, magnitude out, VM out, VP out. Oops, how come? VP, VM. Okay, let's copy this one. Oh, this is not the one. How come? Edit. Okay, this is the one. Okay, I copied this one here. Inverter M4. So simulate. Graph. So let's just see out magnitude, out phase. Set logarithmic and then split. So this amp gain is pretty high, right? This amp magnitude is around 383, pretty large, right? Bandwidth is pretty large because I don't have any load capacitor. So it works fine. Only if we can make a DC bias. Yeah. So so as long as we can supply DC bias here, right? This one, I have a huge 10 times inverter here, right? X10. So this inverter and that inverter has the same logic threshold voltage. So if we apply proper DC bias, then this amplifier works fine. Okay, yeah, there are some efforts to try to adjust the operating point properly. I mean, to some desired point. Say, yeah, there is one